live stream.
Can you ask them if they get the sound?
Actually, my father is saying that there is a problem in the sound, so I guess he's mentioning the echo. Let me ask him. Okay, he's mentioning the echo, so they have the sound, but just they are speaking about the echo.
Can you say something? I'm also live.
I'm sorry?
Come on.
I think I can say something.
Yeah, okay. Test, test, test. Test, test, test. You are able to hear me? Maybe it's like Mahdi who's stopping the voice. Mahdi, can you make sure that you have the audio input and the live stream?
Okay, they can't hear this.
Okay, maybe it's like 20 seconds late. No. The sound works now. Okay.
Ali,
Yes.
can we try sound from the place where you will be standing during presentation?
I guess I'm going to be presenting here. Is that okay for you?
Speak a bit more.
Okay, so hello everyone. Thank you, Eric, for being here to attend my PhD defense. And also, I would say that I really miss room. It was a really nice place, and it was really nice working with you and Omio. Can you hear me well?
Yeah, but it sounds much better when you are close to the microphone. So if you can possible to move the microphone closer.
So it sounds better if I was standing here.
Yes, big difference.
Okay, so maybe I'm going to present like this, and I'll be standing like this.
Mhm. There is a bit of echo. That's probably because of when you touch off the microphone. Yeah,
I'm not sure.
yeah. Since the microphone appears not to be sure if you are signal or noise during when you are to try to cut out.
You turned off the microphone, it's now better. Do you think so? I guess there's no echo anymore.
No, yeah, and it's much better on this distance.
Yes, okay. Then I'm going to present like this. Thank you, Eric. Okay,
I
now we
can
have.
hear you. I can hear you all very well. So if you stay like that, I think it's going to work. So.
Okay. Thank you, Ivona. But now I actually echo.
I think from no, there is also echo coming from.
I'm sorry. I wasn't able to.
I think echo started when Ivona get off mute.
Okay. So
Now it's gone again. Yeah.
Okay, so now we don't have echo. Yeah.
No.
Yeah, that's good, but
I think we have all to go on mute, otherwise there is a very bad echo. But so now I'm going again on mute.
Okay.
So the mic is there. This is the one. If you want to move there, you can put it just there.
But like it's actually very limited. Like this is how much work I have.
Oh, okay. Then put it.
Yeah. Yeah, I'm going to put like this.
Okay.
Can also the audience hear the committee members?
I've been speaking with my family, and I guess they can hear us. So basically, there is Midi who's connected to the Google Meet, and he's responsible for everything related to the live stream.
Okay, very good.
Ok, on t'attend. Ah ouais. À tout de suite. Je pensais que c'était 9h30. T'avais écrit 9h sharp. Hein. J'ai dit 10 fois. Je sais. Oui. Et sinon, je pense que quand vous parlerez, c'est peut-être mieux de venir à proximité chez le micro. Bonjour Étienne.
Oui, bonjour, désolé, j'avais noté 9h30, je suis vraiment confus. Je vous présente mes excuses. Est-ce que vous m'entendez? Oui, bonjour, est-ce que vous m'entendez?
Oui, on t'entend.
D'accord, oui, bah, désolé, j'avais noté 9h30, je suis vraiment confus. Voilà, oui, d'accepter mes excuses.
Pas de problème. Okay, thank you all. I'm David Bomberg, professor at the University of Rennes 1, and I'm going to head this session and to act as a president for the jury of the candidate Ali Fahs for his thesis entitled Proximity-Aware Replica Management in Geo-distributed Fog Computing Platforms. And so for this jury, we have Erik Elmroth, professor at the University of Sweden, Umeå University, and Ivona Bendic, professor at the University of Vienne, and Etienne Rivière, professor at the University of Louvain, and also Shadi Ibrahim, chargé de recherche at INRIA. I think that is a mistake. It's written at the University of Rennes, so so we have to change that. And of course, Guillaume Pierre, professor at the University of Rennes, who is the advisor of Ali. So now we're going to start, Ali, and you have 45 minutes to present your work, and so you can start as you want.
Okay, so hello everyone. First of all, I would like to say that thank for the jury and thank for everyone who have attended this presentation, whether it is in person or whether it is using the video conference. And sorry for the technical issues that have happened earlier. Today I'm going to present my PhD thesis under the title Proximity-Aware Replicas Management in Geo-distributed Fog Computing Platform. This PhD is supervised by Professor Guillaume Pierre, and the research was conducted in the University of Rennes 1 and in IRISA. So, after the revolution of internet, we start seeing a lot of online applications. And these online applications were running using the in-house IT servers. So basically, you will have an application developer who will create the in-house IT server, and after that, the applications will be hosted there. However, this has placed a lot of complicated engineering tasks on the applications developers. So we start seeing a need for a separation of concerns between somebody who will take care of the application infrastructure and somebody who will take care of the application development. As a result, cloud computing has came to liberate the application developers from maintaining the traditional IT servers. However, the advantages of cloud computing doesn't stop at this, because the cloud computing have, first of all, provided us with a solution whenever we want to scale. So instead of scaling up an IT server, nowadays we can, by a couple of clicks, we can scale the application on the cloud. Also, cloud computing have opened a lot of opportunities for other types of applications. For example, for compute-intensive applications, at the beginning, we needed to create a huge infrastructure to hold the application. However, nowadays, we can rent this infrastructure from the cloud using a couple of clicks. So we started seeing a lot of new types of applications like artificial intelligence, like Internet of Things, like streaming, that's based on cloud computing. Sorry. However, same as any technology, the application developer will start exploiting this technology until we reach a certain wall. For the case of cloud computing, we reached a response time wall where we start seeing a lot of applications that are latency sensitive, so they require their request to be treated in a very low response time. And simply, the cloud computing architecture cannot support such applications because the end users are connected to the cloud data centers using the internet, which will induce a latency between 40 to 150 milliseconds. So the research community have address this problem by suggesting fog computing, which will extend the cloud computing with additional layer called the edge layer, placed next to the end user, in a way that the end user will be able to connect to the edge layer, to one of the nodes of the edge layer. And instead of sending the request all the way towards the cloud, they are able to send it to one of the edge nodes. And this will drive down the latency to 1 to 10 milliseconds. So basically what we are doing here, we are supporting the latency sensitive application by bringing computation where the input data was produced. Now, the main difference between fog computing and cloud computing is the distribution. So on the cloud computing, we have seen that we are going to collocate nodes in a data center or in a few data centers. However, in fog computing, we are going to distribute the nodes across a coverage area. This coverage area can be a city center, a university campus. For the sake of simplicity here, we are going to consider the map of France as the coverage area. Now, the end users are able to connect to one of those edge layer nodes, so they will be able to access those resources in a fast manner. And they will be able also to access the nearby nodes in a fast manner. However, this geo-distribution have created a certain variation in terms of inter-node latencies, such that if we take into consideration two nodes which are located next to each other, we are going to have a low latency. However, whenever we take two nodes which are located far away from each other, we are going to have a high latency. And as a result, a latency-sensitive application that require the request to be treated under a certain threshold will have to replicate the application to offer all of the end users a nearby replica in a way that the user will have a low user-to-replica latency. But the main problem here is the fact that we don't have a dedicated fog orchestration engine. And the current fog platforms nowadays are using cloud-based orchestration engines. So those cloud-based orchestration engines does not support proximity awareness, and we are going to end up with a situation like the one presented in this figure, where we don't have proper routing, we don't have proper placement, and we don't have proper autoscaling. So speaking of the orchestration engine, our goal in this thesis, we want to start by an orchestration engine, which is a cloud-based. And after that, we want to modify this orchestration engine to make it suitable for fog. So we decided to use Kubernetes as a proof of concept, and we want to validate our algorithms using Kubernetes. Because Kubernetes first, it's a popular container orchestration engine, and also Kubernetes handles the resource management, and it offers us a lot of features like fault tolerance and like high availability. However, Kubernetes is cloud-based, and this means that Kubernetes does not support proximity awareness, and this is exactly what we want to fix. Now, speaking about the application model, first of all, we are going to consider service-oriented applications that are latency sensitive and that they are monolithic applications. So in Kubernetes application model, we will see that applications are organized as a set of pods, or basically they are the replicas. So we are going to use replicas and pods interchangeably in this presentation. And here, very important note in Kubernetes that any node in the cluster can act as a gateway. So if a user is connected to one of the nodes in the cluster, then this is the gateway node for this user. And in every node in Kubernetes, we have something called Kubernetes services, which will act as a load balancer that will redirect the packets or the request from the gateway node toward one of the application replicas. In Kubernetes as well, we have a scheduler, which is responsible for the replica placement. And we also have an autoscaler, which is responsible for scaling up and down the application. However, all of those components of Kubernetes are proximity unaware, and this will lead us to high latency. So speaking of this latency, we can categorize this latency into three different categories. The first latency that we are going to encounter is the latency from the end user until we reach the first fog gateway. And this is in telecommunication known as the network last mile latency, and we don't have that much of a control over this latency. The other latency is also a network latency, and it's the latency from the fog gateway until we reach the first application replica. And this latency is called gateway to replica latency. And finally, we have, of course, the processing latency, which is the latency induced by processing the request, and it's controlled by normally by the application runtime and by the application architecture. So in this thesis, we decided to focus on the gateway to replica latency because we believe that we can reduce this gateway to replica latency by changing the resource management of the orchestration engine. So simply by changing the way we are going to place replicas and changing the way we are going to route toward those replicas, we can change we can reduce this network gateway latency. So as a result, we are going to create a proximity-aware resource management by designing and implementing proximity-aware routing, proximity-aware placement, and proximity-aware autoscaling. So for the first problem, which is the problem of routing, if we consider a cloud-based routing mechanism, we will see that we will have an end user connected to one of the nodes, and after that we have an application that will offer a set of replicas. So in cloud computing, what we are going to do in routing, we are going to load balance between those replica in a way that each replica will receive the same amount of load. However, whenever we apply such mechanism in fog computing, we will see that this will lead to us routing some requests toward far away replicas. As a result, this will induce high latency. And finally, to solve this problem, what we need to do first, we need to detect which replica is nearby and which replica is far away. And after that, we need to implement a routing mechanism to route the request toward the nearby replica and not the far away ones. So in the state of the art of the first problem, we will see that a lot of people have considered task offloading. In task offloading, we will consider two different homogeneous layers. The first layer is the edge layer, and the second layer is the cloud layer. In contrast, in request routing, we are going to consider the edge layer as a heterogeneous layer in terms of the latency between the user and the application replica. So in the request routing field, we will see that we have one paper that can be compared to ours by Caprice et al. In this paper, they have considered to optimize the battery state, the resource utilization, and the latency. However, they didn't define mechanisms to, first of all, estimate the latency and mechanisms to implement the routing algorithm. So we can say that our contribution, proximity, to the best of our knowledge, is the only distributed system that estimates the internode latencies and then implements the routing accordingly. And the second problem, let's start by the idea that we have perfect routing. So we are going to route to the nearby replicas. So here, we will reach some situations like the one in the figure, where we are going to be forced to route to faraway replicas simply because there is no nearby replicas. And as a result, this will induce high latency. So this bad placement induces high latency, and we need to fix it. First, by detecting the sources of traffic, and second, by placing those replica next to the sources of traffic. And since the workload and the fog is it will vary a lot, this means that we need to update the placement whenever we detect a change in the workload characteristics. Now, in the state of the art of the placement, we will see that there's a lot of people have worked on placement and fog computing and edge computing. However, not a lot of people have considered replicated application, and not a lot of people have considered dynamic placement. Some of the people have considered static placement. And also, there is a lot of researchers that have considered data placement or virtual machine placement. In contrast, we are going to consider service-oriented, dynamic, and replicated application. So whenever we look at this very specific field, we will see that we have two papers that can be compared to our contributions. The first one by Tang et al. And the second one by Li et al., where they have implemented a latency-aware placement algorithm. However, this algorithm, first of all, did not identify the underlying routing mechanism, and also those mechanisms used mean latency as a metric of evaluation. However, we are going to use other metrics for this evaluation. So in our contributions, we have two placement contributions. The first one is HONA, which considers fixed number of replicas, and Voila, which have the capabilities of placing and also auto-scaling the replica set. So HONA and Voila, first of all, they have identified the underlying routing mechanism, which is the proximity, our previous contribution. And also HONA and Voila use tail latency as an evaluation metric. And we are going to speak more about tail latency and further in the next slides. So the third problem that we need to target is autoscaling. And here we need to start by the idea that we have good placement and we have good routing. However, we can reach a point where the number of replicas is not sufficient to support all of the end users. So in this case, we can reach a situation where the number of replica is not sufficient. First of all, in the case where we have a lot of users connected to the same replica, and in this case, we are going to reach an overloaded replica. And in another case, we can have a scattered user base where we have users located in different regions, and we don't have enough replicas to support all of those end users. So we are going to fix those problems by increasing the number of replicas and making sure that all of the users have a nearby replica.
In the state of the art of autoscaling, we will see that a lot of people have worked on autoscaling, however, in Kubernetes, in grids, and clouds, but not a lot of people have considered autoscaling in fog computing, simply because there is another option, which is task offloading. So if you have an extra load, you can offload this load to the cloud. But for latency sensitive application, this is not a valid option because this will induce very high latency. So whenever we look at the field, we will see that there is two contributions that can be compared to ours. The first one is enorm by Wang et al., which have considered a homogeneous edge layer. And there is another contribution, ORCH by Todze et al., that have considered that we can increase the resource pool by adding new nodes to the edge layer. In contrast, our contribution, Voila, we are going to consider the edge layer as heterogeneous, and we are going to consider that the resource pool is limited to what we have. So we can say, to the best of our knowledge, Voila is the only dynamic fog resource manager that considered all of the layers of the resource management. So to sum all of those up, first of all, we have 3 layers of resource management that we are going to target in our work. The first one is routing, and we have created the contribution 1, proximity. The second contribution, the second level of resource management is placement. And here we have created 2 algorithms. The first one is HONA, which will consider a fixed number of replicas, and the Voila, which will place and also have the capability to auto-scale the number of replicas. So in this presentation, we are going to present, first of all, proximity and Voila, because the combination of those 2 will give us solutions for all the levels of resource management. If you want more details about HONA, then you can refer back to the thesis. So let's start by proximity. What's our target problem? Our target problem is the fact that we don't have a proximity-aware routing mechanism, and this will lead us to having high user-to-replica latency. So if you want to dissect this problem into different challenges, the first challenge is, even though that we want to implement proximity, but we don't want to lose the load balancing. So we need to have a trade-off between those 2, proximity and load balancing. The second challenge is the fact that we need to estimate the internode latencies. And if you want to estimate this internode latency, this sometimes may lead to network overhead whenever we have a high scale. And the third challenge is the fact that we are going to integrate an orchestration engine, and we don't want to impact the scalability of the orchestration engine by, for example, invoking a lot of control messages. So let's start speaking about the way that we are going to measure this proximity. First, we are going to use latencies to measure the proximity between 2 nodes. And since we know that calculating the pairwise latencies of all of the nodes will lead to a lot of control messages, which will affect the scalability of the system, we need to try to figure out a way without inducing this overhead. So we decided to use Vivaldi Coordinates, which will first estimate the internode latencies by contacting a few number of nodes. So it won't contact all of the nodes to figure out the internode latencies. So of the advantages of Vivaldi Coordinates, it's very lightweight, so it scales very well. And also it gives us very reasonable estimation. So we have estimated that the average error will converge in the order of 10%. So this is more than sufficient to tell us what are the nodes which is nearby and what are the nodes which is far away. So now how we are going to integrate in Kubernetes. And to understand that, we need to start from Kubernetes itself. In this case, we know that all of the nodes can act as a gateway node, and all of the nodes have a Kubernetes plugin called kube-proxy. Kube-proxy is going to implement a network routes as if they are probabilistic network routes, basically. So for each route from the gateway node to any replica, we are going to have a probability. In Kubernetes, since we care about load balancing, then the probability of selecting different replicas is equal. So we have a uniform distribution over all of those replicas. So from this slide, we need to take 2 things. The first thing is the probability of each replica is equal. So all of the replicas have the same probability. And also that the routing table for all of the gateway nodes is similar. So how we are going to change this? We are going to change this by, first of all, implementing our solution, proximity, as a plugin in Kubernetes. Proximity will be also located in every node in the cluster, and it will take all the information from a kube proxy. So it will be internal communication, and this does not impact the network overhead. And as a result, proximity will implement the routes in the same fashion as Kubernetes. So we'll have also probabilistic routes where each replica will have a probability. Now, the tweak or the twist in this case, what we are going to do, we are going to calculate those probabilities or weights using the latency from the gateway node to the serving node. So the weight will be a function of this latency. And as a result, first of all, we are going to have different weights for different replicas in a way that we are going to give higher probabilities for the nearby replicas and lower probabilities for the far away replicas. And also this will mean that for each gateway node, we are going to have different routing tables. So now how we are going to calculate those weights or those probabilities. So let's try to formulate this problem in a mathematical fashion. What we are trying to do is we are going to start from a deployment phi, where each small phi is basically an application replica. So we are going to try to calculate a probability for each one of those replicas. As a result, we are going to take a member of the set phi, and we are going to map it to a member from 0 to 1. So we are going to create this probability in a way that the summation of all of those weights will be equal to 1. So basically, we are creating a probability distribution function. Now, if you want to use this mathematical model for Kubernetes, we are going to get that the probability for all of the pods is equal to 1 over R. R is basically the number of the replicas. Simply because in Kubernetes, we care about load balancing, and this will give us the same probability for all the replicas. So we will have perfect load balancing. So now we can consider that we have two extremes. The first extreme is load balancing, and we can implement this extreme using a uniform distribution function. All of the replicas will have the same probability. And the other extreme is proximity, where we are going to create a biased distribution, which will give us this proximity. So what we are going to do in the other extreme, in the case of proximity, we are going to give higher probabilities for the replicas that have lower latency. So how we are going to control this trade-off between load balancing and proximity? Simply, we are going to create a mapping function. This mapping function will have two components. The first component is load balancing, and the second component is proximity. For the load balancing function, we are going to use exactly the Kubernetes function, which will give us perfect load balancing. And after that, we are going to connect those two components using the variable alpha. So alpha is a trade-off variable, where here, whenever you look at the equation, if we set alpha equal to 0, this means that the proximity component will be eliminated. And whenever we set alpha equal to 1, this means that the load balancing component will be eliminated. So whenever we have alpha between 0 and 1, this means that we are evolving both of those components to the calculation of the weights. So the application developer will decide how much load balancing he wants and how much proximity he wants, and after that he will give us the value of alpha according to his application specific needs. Now for the proximity function, we are going to consider a decay function. It's a decay function because it's decreasing. And after that, this decay function is a function of the latency between the gateway and the application replica. In a way that it's a decreasing function because whenever the latency increases, this means that the probability will decrease. That's why it's an decreasing function. And now we have created different scenarios for this decay function to study different behaviors for this decay function. So finally, after we have created those probabilities and those routes, we are going to implement them in the routing table. And now we are ready to do the evaluations. So for the evaluation, we have set an experimental setup, experimental test bed basically of 12 Raspberry Pis. So here you can see that at the beginning we started by 12 Raspberry Pis, and later on using Huna and Vola, we have increased the scale to 22 Raspberry Pis. Those Raspberry Pis will run Docker and Kubernetes. And also we are going to implement artificial internode latencies in a way that each node will be a European city, and the latencies between those nodes will be the latencies between those different European cities. Now in the evaluation, we started by a deployment of 11 pods. So basically each worker node will have a pod, and we have used an exponential decay function. And we started by evaluating different values of alpha in a way that for each value of alpha, we are going to transmit 1,000 requests. Now here we have to highlight that those 1,000 requests are transmitted from one single gateway. So the first thing that we have studied is the average round-trip latency as function of different values of alpha. So we are going to transmit those requests, we are going to calculate their latency, and then we are going to plot the average round-trip latency. Whenever we start by alpha equal to 0, we will have the case of Kubernetes. And in this case, we have perfect load balancing, but obviously we have high latency of 16 milliseconds. This is the average latency. And after that, whenever we start evolving alpha and the calculation of the mapping function, we will see that the average round trip latency will start dropping as we increase the value of alpha until we reach alpha equal to 1. And in this case, we'll have full proximity. As a result, we will have a very low value of the average round trip latency. Now, to understand why we have this drop in the latency, we have plotted the distribution of the request as function of the different replicas. So in the below graph, we will see we have plotted in the y-axis the number of request packets as function of the different replicas sorted from the replicas with the lowest latency to the replica with the highest latency. So we can see here at alpha equal to 0, as expected, we have very good load balancing, and all of the replicas have received almost the same amount of load. Now, whenever we start increasing the value of alpha, we are going to start setting this bias toward the nearby replicas. And this means that we are going to receive more load at the replicas which have lower latencies. And this will continue, the bias will continue increasing until we reach alpha equal to 1, where we see that we have full proximity. We have eliminated almost all of the pods that have a higher latency, and only the first 3 pods are receiving load. Now, this case is basically the worst case scenario for load balancing. In the case of this one, like for alpha equal to 1, simply because we are transmitting all of the load from one single gateway. However, if we transmitted this load from different gateways, this means that we are going to have a more distributed load balance while keeping the proximity. So in this case, we decided to continue our work in HONA and in Voila using alpha equal to 1. However, we decided that the load balancing problem should be solved not only in routing, but also should be solved in the placement and autoscaling problems. So let's now continue to Voila, our third contribution. Here I have to mention that this work was performed in collaboration with Professor Erik Elmroth from the University of Umeå in Sweden. So what's the target problem of Voila? We don't have, first of all, proximity-aware placement. We don't have proximity-aware autoscaling. And this will lead to, as explained previously, to high latency and to oversaturation. So if you want to dissect this problem, we will see that we are dealing with latency-sensitive application, and those applications will set a threshold. The meaning of this threshold is basically that if a request is treated in more than this threshold, this will lead to normally a bad quality of experience for the end user. So we need to keep all of the requests under this threshold L0 defined by the application. Now, whenever we see the placement problem and fog computing, we will see that a lot of people have tried to use mean latency metric as a metric for evaluating which placement is better. However, we have seen that whenever we use the mean, we can reach a case where we have end users that have a very low latency and end users that they have a very high latency. And as a result, we have a really good mean, but we don't have a fair distribution over the end users. So some of the users will have requests treated over the latency L0. So we decided to choose another metric, which is tail latency, that is defined as the percentage of requests with latency greater than L0. And after that, we need to eliminate this tail. So this is the tail of the distribution. It should be eliminated in the placement that we choose, or at least it should be reduced. And this tail latency will give us better fairness between different users. Now, the second challenge is the fact that we have a limited number of resources assigned to each replica. And this means that we have also a capacity cap or a saturation point for this replica. So whenever we reach a point where we are going to exceed the maximum capacity of this pod, we are going to reach an overloaded pod. And this means that the request will be queued. And this means that we are going to have higher latency. So we need to avoid situations where we have overloaded pods or replicas. Finally, we have the challenge of non-stationary workload because we are working with fog computing, which is very dynamic. And this means that we are going to have variation in terms of load. Now, Voila will target all of those challenges and will provide us a solution that will solve all of those challenges at the same time. To elaborate more about the third challenge, let's consider that we have a geo-distributed load. In this case, we have taken the load from a telecommunication company in Italy. And after that, let's say that we have accumulated all of the load coming from different regions in one plot. So basically, this is the overall plot, which will represent what an online application hosted on cloud will see. as low. So we are going to see the normal day-night pattern where we have a low number of requests during the night and a high number of requests during the day. However, here, whenever we look at the hours during the day from 8 until 20, we will see that the load is almost stable. However, whenever we dissect this graph into different regions, we will see that different regions will behave differently. So in this case, for example, the commercial area will peak at 12 and 4 p.m. However, a residential area will peak at 6 to 7 p.m. and a nightlife area will peak at 11 p.m. So we need to treat the placement problem and the autoscaling problem according to those variations, not only according to the variation in terms of time, but also according to the variation in terms of location, because we want to avoid those peak hours in certain regions. And as a result, Voila exactly treat this problem. Now, how Voila will work? First of all, Voila will consider that we have a cluster of unknowns and R replicas. And Voila will start by monitoring the system and collecting information about the system. The first type of information is a cluster information that is collected using Kubernetes. And in this case, this consists of the nodes and associated variables for the nodes. And also the replicas and associated variable for the replicas. Second, we are going to collect latency information, also using Vivaldi Coordinates. And then Voila will organize this network around the trip latency and a matrix L. And finally, we need to collect performance and traffic information, and this is collected using proximity, our previous contribution, where proximity will provide us with a summary of the number of requests redirected by each gateway and the number of requests received by each pod. And also it will give us a probability matrix, which is basically for each row, it's the weights for each gateway. Now, after we collect those information, we need to evaluate the placement. And in this case, Voila will define a new variable called epsilon. This variable epsilon will represent the percentage of slow requests. And those slow requests have two different definitions, let's say, or two different type of requests that can be identified as slow requests. The first one are the requests encountering high round-trip latency greater than L0, which means that this is a latency saturation or proximity violation, I'm sorry. And also we can have the situation where we have saturation violation, where the requests are redirected toward a replica which is already overloaded. So after we calculate the value of epsilon, we need to make sure that this value of epsilon is less than epsilon 0 defined by the end users. So the end user will say that, okay, this is our quality of service constraint. The epsilon, the number of percentage of slow requests should be lower than a value epsilon 0 defined by the user. And this is our quality of service constraint. Now, in simple terms, we are going to calculate those using a certain model that we have created where we have a general matrix, and after that, we are going to derive out from this general matrix a placement-specific matrix. And this will help us to speed up the evaluation of the placement. Also, more details on this for in the thesis. Now, how Voila works. Voila works in a periodic fashion. So we have a check function. So let's say we have an application already running with the replicas, and we have this flex check function, which will be called every certain amount of time. This check function will first calculate the value of epsilon for each application. And after that, we need to make sure that we are respecting our quality of service constraint. So if the value of epsilon is less than epsilon 0, this means that we are respecting the quality of service, and this means that we don't need to change anything. However, if epsilon is greater than epsilon 0, this means that we have a violation. First, we need to determine the type of this violation, whether it is a proximity violation, where we are going to call fixed proximity, and whether it is saturation violation, where we are going to call fixed saturation. Now, those two fixed functions will behave in a similar manner. So they are almost very similar algorithms. However, the way we are going to compute certain variables inside those fixed functions are going to be different. So to elaborate more about this, we are going to show the fixed function. So in this case, first of all, what Voila is going to try to do to fix the violation, it will try to do a replacement. And by replacement, we mean that we are going to preserve the number of replica, but we are going to remove a replica from one node to another, trying to solve this violation. So in the replacement, the first thing that the fixed function will do is a replacement, or try to do a replacement. So we are going to detect the origin of the violation from where this violation is coming. And then we are going to get a set called TBR, which is to be replaced. And this consists of the replicas that we believe that should be moved from one node to another. And after that, we are going to get another set, which is TBT, which is to be tested. And this is represent the nodes that we think that they are potential, and we think that is going to give us a solution for this problem. Now, the origin, detecting the origin and calculating TBR and calculating TBT, it depends on the type of the violation. So after we do this, we will start trying to remove this replica from the node where it's located. So we are going to take a replica from TBR, move it from the node where it's located to TBT, which is one of the potential nodes. And we are going to do those tests where we are going to calculate the value of epsilon for this new placement that we are creating. Whenever we finish all the tests, then we are going to check if there is a placement or a replacement that will solve our violation. And if this is the case, then this is perfect. This is a cheaper solution for the violation. And then we are going to return this placement. Otherwise, if this is not the case, then this means that we can't fix it using replacement, and we need to fix it by scaling up the scale of this application. So now, for the autoscaling function, the beautiness of Voila, it will consider the autoscaling function as a continuation of an already studied problem. So you have studied everything related to this violation and the previous functions. And after that, we reach a point where we are going to call scale up, and we are going to give it the set of interesting nodes, TBT, which is the potential nodes. So in simple terms, how we are going to scale up, we are going to try to add one node at a time from the set of TBT. We are going to test all of the nodes in TBT. If we find a solution, then we are going to return it. Otherwise, we are going to keep adding replicas until we find a solution for this violation. Now here also we have another algorithm, which is the scale down algorithm. And at a certain point, the scale down is triggered whenever we figure out that the number of replicas is higher than what is necessary. So we are going to scale down. This algorithm is also available in the thesis if you want to check. So finally, after implementing all of those algorithms, we are going to test Voila. And we took two different approaches. The first one is the approach of simulation, where we have used simulation to validate the scalability of the approach. And also we have evaluated the algorithms using a test bed to validate the feasibility of the approach. So on the test bed, we have 22 Raspberry Pis that are running Docker and Kubernetes. Here, Voila is implemented as a set of Kubernetes plugins. So we have different functions implemented as plugins in Kubernetes. And after that, we are going to use the same load that we have presented in the first slide, where we have a realistic geo-distributed workload from a telecommunication company in Italy. And finally, we are going to emulate realistic internode latencies using the TC command in Linux. So the first evaluation using the test bed, we are going to replay a load of 28 hours in a way that this workload is replayed for each hour in 2 minutes. So in the first graph, you will have the geo-distributed load, the overall distribution of the load. In the second graph, we have the deployment size. And in the third graph, we have the percentage of slow packets by type. So whenever we look at the request rate, at the beginning and the early hours in the morning, we will see that the load is very low. However, we still detected that we have new sources of traffic. And as a result, Voila will solve this violation, this proximity violation, by increasing the number of replica to amount to all the end users. Later on, we will see that from 6 a.m. till 9 a.m., we have reached a point where we have an exponential increase of the number of requests. And this means that we are going to have a saturation violation. And as a result, the number of replica will be increased to amount to those increased requests. Now, during the day, which is what's interesting, that we are going to have almost a stable load. However, since we have those different locations that will peak at different times, this is why we are going to see that we have different replacements at different times to fix those peaks at different regions. And during the night, the load will drop, and as a result, the number of replicas will drop. So from this slide, we can conclude, first, that HUNA handles the non-stationary load. Second, that HUNA optimizes the resource utilization by using the minimum number of replicas. And third, we will see that Voila was able to accept or to validate the quality of service constraint. And we have reached a point where we have more than 98% of the requests are served by nearby and non-overloaded replica. So this means that we are assuring that 98% of the requests are treated with a low latency. Now, for the simulation, let's consider the scalability analysis of the simulation. So we have tried those algorithms over different scales for the system, for the cluster. We started from 100 nodes until 500 nodes. In the blue graph, we have calculated how many placements we can evaluate during 1 second. And in the purple graph, we have calculated the number of placements that we need to evaluate to fix a violation. So whenever we start at 100 nodes, we can see that we can evaluate a lot of placements. However, whenever the system size increases, this means that the number of replicas will start to drop because the placement evaluation is more complicated, so we need more time to evaluate it. However, since whenever we are increasing the size, the placement problem is getting easier and easier. That's why we are not going to see an increase in the number of placement we need to evaluate to get a solution. And as a result, even for 500 nodes, we can find a solution for this violation in almost a little bit over 1 second. So basically, this is we can prove that this algorithm to a certain point work at a scale. So in conclusion, first of all, Fog Orchestration Engine should implement proximity-aware resource management, simply because we need to ensure the end users that they are going to get low user-to-replica latency. And this is done by, first of all, implementing proximity-aware routing, proximity-aware placement, and proximity-aware autoscaling. Here also, we need to use metrics like tail latency to ensure that we have fairness between end users. And also, everything should be implemented dynamically because we have a very dynamic load. Now, in the figure, we can see that we have the stack of Voila, where we will see that we have addressed all of the layers of resource management. And we have used our previous contributions in Voila. So basically, we have sequential work where we are going to use our solution and all of the new contributions. So finally, the take-home message: the Voila stack was able to guarantee more than 98% of the requests are routed toward a nearby replica and non-overloaded replica, which means that we can ensure this low gateway to replica latency. Now, for the future direction, we have an already undergoing future direction, which is a collaboration with the Linköping University in Sweden. And this future direction, we are going to consider the idea of having a spare node. So in a system, we will have dedicated nodes, and we will have leverage over spare nodes from another fog provider, for example. In this case, this approach will create an interesting problem in resource management, where we have a trade-off between performance and cost. So it's very interesting future direction for us. The second future direction is same as cloud computing, where we start seeing more than one cloud provider, and until the moment we reach a point where we have cloud federation and multi-clouds. We are anticipating that in the future we are going to have fog provider, and we are going to have more than one fog provider. So it makes sense for us to create this federation of fog providers. However, not like in a cloud where we have those framework for the federation, and for computing we don't have those frameworks, and as a result, we need to create those frameworks. So this is also a very interesting research topic. And the third future direction, we believe that we started seeing a niche in the market for specialized nodes. For example, for AI, where we see hardware accelerators and FPGAs, and for gaming, for example, and for graphics. So we start seeing some nodes which are specific for certain nodes. And in the future, we are anticipating that a fog platform will be composed of the compute nodes, which are the regular nodes, and also specialized nodes. So here, the resource management problem will be extended to, first of all, routing, placing, and autoscaling, not only according to the location of the node, but also according to the node specialization. Finally, and very interestingly, we have considered monolithic application because we were focusing on the provider infrastructure. However, later on, it's a very interesting problem to see different types of architecture for the applications. So, for example, for microservices, resource management in microservices will take a different approach at the application layer. And here, for example, we are not going to route only to those replicas of this application, but also we are going to route inside the application in the back end. And also for the placement problem, we can see that it's not only a one placement problem, it's a set of interrelated placement problems for different components of the microservice. And finally, for the scaling, in a microservice, we are not going to scale up all the components, but we are going to scale up specific components. So all of those are very interesting questions in terms of resource management. Finally, we can say as a closing statement that we started from a cloud-based orchestration engine, and this cloud-based orchestration engine was not proximity aware, and we have seen that we can make it fog aware by adding those proximity awareness. Those are the list of my publication, and I would really like to thank you for listening to me, and I'll be very happy to take your questions.
Thank you very much for your presentation. And now we are going to start the session. And in particular, we're going to the reviewers. We have Gona Brandit, the reviewer. We are used to start by the reviewer is the furthest. So Ivona can start, please.
Hello. So first of all, Ari, thank you very much for the presentation. And thank you very much for staying calm despite all these technical issues. So I enjoyed your presentation. I didn't understand now the last sentences, but may I start now questioning?
Yes, you can.
Okay, thank you very much. So first of all, what I would like to know, you mentioned that you use Kubernetes as the technology here. So let's imagine Kubernetes were not there. What would be the second best?
Okay, so as we mentioned that we use Kubernetes as proof of concept and the goal of the world. So we believe. I'm sorry. Can you turn off the computer? Echo. The mute.
Okay, I will do so.
Okay, so we mentioned that we are using Kubernetes as a proof of concept and not as a goal of the research. At the end, this is a research project and not a technical engineering task. However, answering your question, what would be the next best? I would say we have different varieties of orchestration engines that are very popular. For example, we have Mesos, we have Docker Swarm, and recently, actually, we have been contacted with somebody in India who's interested in implementing our algorithm in Nomad.io, which is also another orchestration engine. So we believe that our algorithms, we need to, first of all, understand the orchestration engine, and after that, we can figure out where exactly we have to implement those algorithms. However, which one is best? To be honest, this is a relative question or a subjective question, and it depends on the use case, I would say. But Mesos, Docker Swarm, those are very good contenders.
Thank you. If you would have to summarize the characteristics of the orchestration engine that you would need here or you assume here, how would you describe this orchestration engine? So what are the characteristics?
Okay. So this is actually I would say. I'm sorry. I'm sorry.
Okay, sure.
So in this case, I would say that any cloud orchestration or a cluster-based orchestration engine would be okay for our work because, of course, we don't want to start doing everything from scratch. So we are expecting an orchestration engine that have certain capabilities that we are going to need. For example, in Kubernetes, we didn't implement a scheduler, but we have influenced the behavior of the scheduler. And the same thing for routing, and the same thing for autoscaling. So in this case, we need an orchestration engine, first of all, that will avoid, which is reliable, which is fault tolerant, which is offers high availability, and offers a lot of other features that we are going to use, whether in cloud or whether in fog. So any orchestration engine which is to a certain point reliable and offer those features would be a good contender to implement our work. Have I answered all your question, or do you need something more specific?
No, thank you very much. I'm fine with that. So another issue that I would like to discuss with you. So what we experience nowadays is more or less, I would say, fusion of computing and telecommunication facilities. So if you think about 5G or upcoming 6G, where you have the telecommunication with very low latency, almost ultra low latency, where you have requests up to, I don't know, a few milliseconds. So how does the proposed approach fit into the concept of this, I think it's called now tactile internet, where you use all these ultra low latency applications like virtual reality, smart cities, and so on. Do you exclude it? Or do you consider only internet connection? So where are the boundaries? So where are the limitations of the approach that you have presented today?
Okay. I guess I understood your question in the right way, that you are mentioning, for example, different architecture for computing. For example, not all of the people are using the same infrastructure, where some people, for example, consider fog computer as fog RAM, where it's basically radio access network, and after that we are going to add compute nodes in the radio access stations, and other people consider more than one layer. So in this case, my work, I believe, to a certain point, and this is an anticipation, that it can fit in all of those infrastructure. And the reason why, because we are working at a different abstraction layer than the infrastructure itself. So we, for example, if you are speaking about the physical layer, we are running on top of the physical layer at the data link layer and at the data transport layer. So basically, our work is not limited in terms of the underlying infrastructure, which is basically the way the nodes are deployed or the way the nodes are connected, whether using 5G or whether using Wi-Fi or whether using simple Ethernet cables. So our work is at a different abstraction, and we are going to calculate those latencies, whether it's 5G with less than 1 millisecond per hop, or whether it is Wi-Fi where we can have 5 milliseconds or 7 milliseconds per hop.
Okay, thank you very much. Another question is considering the fault tolerance of your approach. So I think in one of your answers, I don't know, the first one or the second one, you mentioned that the whole infrastructure like Kubernetes offers you the fault tolerance.
Yes,
so my question is, how do you deal with fault tolerance in your approach? Is there any, intent to deal also with fault tolerance? Do you rely only on the fault tolerance of the underlying infrastructure? So what is the solution that you, because you didn't mention the fault tolerance at all?
Yes. Okay. So for this, mute again.
Okay. Yeah, I always forget it. Sorry.
Don't worry. Okay, so for this question, we can answer it with two faults. The first thing is that Kubernetes, to a certain point, offers us a fault tolerance at the level of the pods. So for example, at the level of the nodes and the pods. So if one of the nodes failed, then Kubernetes will automatically detect this failure. And after that, Kubernetes will automatically move replicas from this failing node to another node, which is still available. So this is the first level of fault tolerance that's also supported only by Kubernetes. However, in our case, the fault tolerance is bounded by the calculation of the latency. So basically, whenever we have a replica failing or a node failing, then this will be quickly detected using the network estimation. So whenever we have a failure, we will see that the latency from the two nodes, the nodes that have failed and the node that's still working, will start increasing. And as a result, automatically the placement algorithm and the autoscaling algorithm and also the routing algorithm will detect this change and also will move the replica to another node and also will route to another replica. So this is implemented indirectly in our system, simply because we are calculating the latency. Now, of course, we have limitation whenever it comes to the fault tolerance, because, for example, in the case of Kubernetes, if the master node where we are implementing most of our work have failed, then we don't have this high availability implementation in our work. However, we can argue here that we can implement our work as Kubernetes controllers in a way that whenever we have the Kubernetes high availability system running, then it will automatically redeploy this controller in a different node. But yeah, definitely we can agree that fault tolerance is something that is limitation to our work, and it will be a very interesting future direction.
Okay, thank you. What you did not mention in your talk is the type of computation that you use here. So when we talk about fog computing, we have different types of computations. Yeah, most recently, of course, we have machine learning applications, geographically distributed machine learning applications, where you have model learning somewhere on cloud server, and then you have the inference on the edge. Or another very popular computation model that we have nowadays is also code offloading, where we offload the code to nearby edge nodes in order to save battery or in order to save time. So which type of computation did you use in your experiments? And this is the first part of the question. And the second part of the question is, do you think that different types of computation can also influence the requirements on replicas?
Okay, that's very interesting. Okay. So first of all, answering the first question is what type of computation that we have considered. We have considered service-oriented, latency-sensitive applications. So we are expecting that this computation will be a computation in terms of a CPU and memory usage, where we are going to compute a certain task, and after that we are going to return this task as quickly as possible. So this is what is the computation that we are imagining. However, to a certain point in our work, we have considered that we are not going to interfere with the application layer. So the application layer is something that's controlled by the application developer. And in this work, we try to target the infrastructure that is underlying this application layer. So that's why we didn't elaborate more on the way of the computation that will be done. So as you can see in our thesis, we have mentioned that we are going to use an application which will simply return the IP address of the current replica. So it's as simple as this, because we are not going to go into details in terms of the application layer, and because our focus was basically the infrastructure and the resource management of this infrastructure. So here, if you want to split those two problems into two different parts, we will have, first of all, what the cloud provider or what's the fog provider have to control, which is the resource management. And also we have another part where we have optimizations in terms of the application and processing time. And this should be controlled by the application developer. So same as in cloud, where the cloud will give you assurance in terms of reliability and latency and all of those. It won't give you assurance in terms of how the application is deployed, because this is the job of the application developer. So that's why we didn't go into details in terms of computation. Now, if you want to speak about how this can affect our approach, we will see that yes, definitely this is a limitation to our work. Yes, definitely this can affect our work. However, we believe that no matter what's the type of computation that will happen, we are still need to optimize the infrastructure. So yeah, I believe, for example, if you are going to consider a set of, let's say, a server that have to communicate with a database, then this type of computation where we need to go and get a query from a database will definitely affect the time we need for the processing latency. So in this case, we can answer by twofolds. The first thing is that this thing is another problem that need to be investigated more. And also, we can say that to a certain point, still, if we have such an architecture, we can still use our work in routing, placing, and autoscaling those databases. So to sum my answer up, we have worked on the infrastructure, and we can consider that each type of computation that we're going to do, whether it's for artificial intelligence or for streaming or for other types of application, it will be another problem, but at the application level. So this is, I guess, will answer your question.
Okay, thank you very much. The next question is considering your quality of service model. Maybe you can go back to slide 26. I think it would be easier for me also to talk about my question. Yes, this one. So the first question is, obviously you need a lot of data to check whether the QoS is violated and to decide about the new placement.
Yes,
So the first part of the question is, where do you get the data from? And does this measurement not make your system intrusive? Means a lot of measurements, you need a CPU, so you over-manage your system by measuring. So how often do you measure? Do you measure every second? Do you measure every 5 minutes? Do you measure all the time, or do you measure only when certain values are changed? So which type of measurements do you use here? This is one thing. And another is how adaptable is whole quality of service check algorithm? Do you consider here highly volatile systems where things change all the time, so you don't, you are not active on the QoS, or do you have the same measurement procedures all the time, no matter whether you have high volatility or low volatility? So what is the nature of this algorithm?
Okay. So first, So first of all, regarding the measurement that we are going to do, we have 3 different types of measurement. The first one is the cluster information, which can be obtained easily from Kubernetes. So this is basically a call to the etcd etcd of Kubernetes, which is a component inside Kubernetes. Now, most of the time, etcd is a component that's located in the master node. And this means that we don't need to have network communication, but we just need to internally communicate with it etcd to get the information about the nodes and the replicas. The second information is Vivaldi Coordinates informations. And here Vivaldi Coordinates uses a gossiping algorithm. And this means that this gossiping algorithm, first of all, it's always running, but it's running at a very slow rate. We don't transmit a lot of requests to collect those informations. And it can converge very quickly to have consistency. So in this case, we have an agent of Vivaldi inside the master node as well. So Vivaldi will be working, and calculating the latencies, and after that we have to execute one call to get the collected information by Vivaldi. And Vivaldi have been proven to be very, very lightweight. So we can show this in the previous work where we have calculated the CPU usage and the RAM usage, and also in terms of network, we can also show you the simulation of the gossiping algorithm and Surf, where it shows that we are not going to send a lot of requests and we are going to converge very quickly. And then the third type of information, where I guess this is the main concern for you, which is basically collecting the information from proximity. And here we also have used the Surf as the tool to collect those information. So Surf will offer us a lot of tools. For example, we have used, in this case, we have used a query to collect those information, where basically proximity will make them ready. And after that, we are going to send a query, and the reply will contain all the information regarding the number of requests and the number of received pods. Now, in this case, we can say that first of all, this can be implemented also using gossiping. However, because of not having enough time, we didn't implement it in a gossiping mechanism, but we have just used simply sending a query and receiving a reply. However, this can be improved on by implementing a gossiping algorithm. Now, regarding your question about how often we are going to do those calculations, and this is a very good question. What we are going to do is we are going to collect those informations every certain cycle, which is decided by the application developer and decided by the person who is controlling Vola. So this is, to a certain point, is variable, but normally we do those collections every 30 seconds. So we are going to collect the information regarding the traffic and information regarding the latency and regarding the nodes every 30 seconds. However, here we can argue also that different types of information can be collected at different times. And answering your last question about the volatility of our approach, no, we are actually always collecting those informations. It doesn't depend on the change of the load. However, I believe that this is a very, very interesting approach where we can try to collect all of those information whenever we detect a certain change. So whenever we detect a certain change in a certain node, then this means that we are going to collect all the information. So this is also a very good future direction. However, we haven't implemented this in our work.
Okay, thank you. And my last question is, so obviously what you're trying to achieve here, or one goal of your PhD thesis is to give a kind of a programmability to edge systems, right? So to be able to set up edge system somehow in a balance to costs and also the quality of the system. So where would you position yourself? On a scale between 0 and 100. 100 is a totally Netflix-oriented system where you pay 10 euros a month and you get certain edge system that can do certain things. And 0, everything is done manually. Where are you now after having done your PhD with your system?
Okay. That's very but I don't know how to exactly give you a number between 0 and 100, so maybe I will explain it in a more generic way, that our systems have a certain control that the users should not interfere. However, what we are trying to do exactly here is the fact that we cannot have complete control over everything, because at the end, in fog computing, we are going to expect different types of application, and those different types of application have different requirements. So it's not we are going to say that, okay, we offer this model and all of the application should conform to this model. However, what we are trying to do is we are trying to, first of all, create this layer where, okay, the user should know this and should give us this, and after that we are going to take care of everything else. So here, what's actually interesting is that we don't start, for example, in Voila, we don't say that for the user you have to decide the number of replicas. We start from application-specific requirements, which is basically the size of the replica and the latency threshold. And after that, we are going to take control over how many replicas and the placement of replicas that we are going to implement. So here I would say that we are going to create something where the user will give us the parameters of the quality of service that he wants and the quality of experience that he wants, and after that, the system that we are going to create will take care of everything, almost everything rest. So this is, I guess, where we are.
Okay, very diplomatic answer. Thank you very much. So that's from my side. Thank you very much.
Okay.
Thank you, Ivona.
Thank you very much, Ivona.
Etienne, if you can start your questions, please.
Okay, can you see me?
Yes.
Okay. Thanks, Ali, for the very good and very clear presentation. I would like to apologize for being late. I messed up with my agenda. So I enjoyed reading your document. It was very clear. You had a very good coverage of all the background material as well. So it's not always easy to understand contributions that are made for cloud orchestration systems like Kubernetes, and here you provide the reader with all the necessary background knowledge that is necessary, and that's positions your work very well. So I do have a number of questions, a few of which have been already asked by Ivona, but I will not ask them again in that case. So my first question is regarding the assumption you make for the applications or the services that you will host at the edge, and you say and you wrote that in one of the slides, that any node can act as a gateway for the application. It means that any node can serve any request from any client. So this seems to me to be a relatively strong assumption on the applications, in particular when you have some state. I mean, you mentioned that one of the target applications could be gaming, for instance. Okay, so even a very simple game like a Pictionary online or something like this would probably require some state. So it means that. So I would like to know your opinion on that. On that assumption, and if it is an assumption that can be lifted by modifications to your systems, or if it is a very fundamental one. And what could we do about it if we want to support applications that require some state?
Okay, that's a very good question. Thank you, Etienne. So at the beginning, let's start by the fact that yes, we consider that in this work, we consider that we have stateless applications to a certain point. And this means that we are going to have, we don't have the state, but that doesn't mean that our work does not support any application that does have a state. Because here also you'll go back to the focus of this PhD and actually the other layer of optimization that we'd have considered as a future work. So first of all, our focus of the PhD is the infrastructure. And that's why we didn't consider state in the application, because we believe that first of all, maintaining the state and maintaining consistencies is a very interesting research problem. However, it wasn't the scope of this PhD. Now, to answer your questions about regarding the state, first of all, we can use something called, maybe I'll go a little bit technical here, but we can use something called IPVS in Kubernetes, where we can target a specific replica. So this is also implemented in Kubernetes. However, here we have a problem where we are, whenever we start by Kubernetes by nature consider the pods as something which is mortal. So basically the pods can fail at any point, and Kubernetes have the rights to remove those pods. So whenever you want to create an application on top of Kubernetes, you need to take into consideration that you have to work in a certain way, that the pods can be deleted, for example. And here we have two different problems whenever we start considering the state. First of all, if you want to use IPVS to route the packets to a specific replica, what will happen whenever this replica will be gone? You are forced to move from one pod to another pod. And also, what will happen whenever we delete one of those pods? So this basically is a problem that can be fixed in Kubernetes, and here I can cite or refer to some people who have been working on this technically with Kubernetes, and they have told me that in terms of the state, we have two different solutions. The first one is by creating a key store, for example, which is the traditional way of saving the state. So the state will be located somewhere else. There is a communication between the service and the data store to save the state. And another way is basically whenever we save the state of the application in the end user device. So each time we send a request, we are going to send the state with it. So those are the two different solutions. Now, creating this stateful application and making it proximity aware also is a very interesting research direction that simply is one of the limitations of our work, because also we have focused on the infrastructure and not exactly the application model.
Okay, well, thanks for the answer. So you give two possible approaches. One is indeed to store application data at the client, and to use a remote key value store or cloud storage. Okay. So there is a lot of work actually on caching for stateless data, or well, not stateless, just the data that is not mutated, and in particular in content distribution network, CDNs. So you mentioned CDNs in the document once on page 58, if my notes are correct, but you do not relate your work so much with respect to what is done in actual CDNs. So can you maybe comment a bit on what are the differences between CDNs and the different policies that are applied in CDNs and your own policies?
Okay. So let me start by the things that are implemented in common between the container distribution networks and content distribution network, and between fog computing. So both of them are geo-distribution, And here, I guess one of the main differences between content distribution networks and fog computing is the computation type. So basically, in content distribution networks, we will have a certain cache that we are going to get. So on the content distribution network, we are focusing more on the bandwidth, not exactly on the latency. However, in fog computing is something that is much closer to you, and the main reason for fog computing is not only bandwidth but also latency. So I would say this is the main difference between content distribution networks and fog computing.
Okay. So my next question is related to the fact that you will have this infrastructure, this fog infrastructure, and it will be, you have this combination of core clouds and a collection of edge clouds, and very likely it will not support a single application. Okay.
Yeah.
So you will eventually have to handle multi-tenancy. Okay. It's probably not very realistic that for a single application you have all these servers. Well, it could be. I mean, we have mentioned the example of Netflix before, and Netflix actually has its own fog infrastructure with this collection of edge racks, because they have a scale that allows it. But most likely, for the type of applications you mentioned, you would have to support multi-tenancy.
Yes.
So this is something I didn't really see mentioned or discussed in the thesis, and I would like to hear from you about the scalability of your approach, not only in the terms of the number of nodes, but in the number of different applications that are running concurrently on the platform. So, is it something that would scale, or is it something that would require some further work to make it scale? So, yeah.
Okay, so I guess here I have to answer you by each contribution that you have created, or at least by proximity alone and by the other contributions alone, which is HONA and Voila. So first of all, let me start by telling you that we have done the evaluation in a single application because we want to create evaluation which is clear and very short, where we are going to focus on how the system will behave with this application. However, in our implementation, all of the contributions that we have created can handle more than one application, and this is already implemented and it's already running. So for the first part, which is whenever we have more than one application in proximity, I would say that in proximity we are going to handle this exactly the same way that Kubernetes handles more than one application, because simply in proximity we don't need to collect information that are specific to this different application, but we are going to collect the internal latencies, which is something related to the infrastructure. So in this case, what we are going to do, we are going to collect that we have this and this and this application from Kubernetes, and we change the IP tables or the routing table in Kubernetes. So in proximity, I would say it will scale as much as a kubeproxy scale, which can be thousands of applications. So this is the first part. The second part, whenever we start speaking about HONA and about Voila, where we are going to collect informations that are specific to the application. So each application we have to collect the number of requests that are redirected toward this application and the number of requests received by different replicas in this application. Then I guess at this point, increasing the number of the applications may to a certain point impact the scalability of the approach. Now, to be honest with you, how much, I haven't calculated exactly how much, but we have implemented our algorithms in a way that whenever, for example, in the slides where we have the informations, the first information is not impacted a lot by the fact that we have more than one application, because simply is an internal call between the master node and the etcd in Kubernetes. The second one also is same as proximity, where we have something related to the cluster and not related to the application itself. However, in the third part, here we have calculations that are different according to different applications. So we have implemented the proximity to collect all of the informations of all of the applications at the same time. Now, at a different scale, I can see that maybe this will need more optimization to have a better collection of the information. I can agree on this part. And also, I can agree on the part where if we have a lot of applications, like for example, if you go to 1,000 application, maybe the calculation of placement, because we are going to calculate and evaluate different placement at the same time, maybe it will be a little bit computational, a little bit heavy. However, this is also only an anticipation, because we haven't exactly reach a point where our algorithms are at the production stage, where we need to calculate the scalability for different applications. So we were just studying the algorithms themselves, and we didn't optimize those algorithms in a way that they are ready for production.
Okay, thank you. Could you maybe just as a quick follow-up, so wouldn't it be simpler to just consider that you only have partial information? I think specifically of this assumption you have that is typical in Kubernetes, is that for any service, the collection of pods that implement this service is known from any node. Okay, so this makes lots of sense in a data center, but here you have relatively low power nodes that are Raspberry Pis, and as soon as the application number grows, then this number of service to pod allocations will grow as well. So is it really necessary to know it on all nodes, or could it just be cached for the applications that are actually used by the users connecting there? I'm
sorry, you can continue your question. I'm sorry.
No, I'm fine. You can comment.
Okay, I'm really sorry. So here I have to mention that, first of all, proximity will run at every node. However, Hona and Voila will run only at the master node. So this is the main difference. So Hona and Voila are centralized, however, proximity is distributed. Okay, so in terms of the information collection, we are collecting the information in one single node whenever it comes to Hona and Voila. In terms of proximity, it's distributed, so it's collected everywhere, but using Vivaldi, which is done using gossiping. So yes, we are already doing this. And regarding the comment of the using Raspberry Pis, we have used Raspberry Pis for the testbed. However, that's not necessary that we're going to use Raspberry Pis in the implementation. So in this case, even if we have a lot of applications, if you have a powerful computer as the master node and all of the other nodes are very small, this is a very reasonable and very valid or feasible implementation, where we have a powerful master node and other small minion nodes, let's say.
Okay, I have a question regarding the use of network coordinates. So I think the use of network coordinates is a great idea. It's something that clearly helps determine what is the latency between different nodes without having to do some heavy probing. But I actually have two questions that are linked. So the first one is, how do you calculate the coordinates for the clients themselves? Okay, so because you need to position clients with respect to the edge servers or edge sites. Okay, and the second is, do you assume something that is purely peer-to-peer, like all the nodes calling themselves to estimate their latencies and relax this Spring system that forms Vivaldi, or do you consider a few beacons that are known and that allows to bootstrap these coordinates? So the first question, how do you do it for the clients? And second, do you use a pure P2P system or something that uses beacons?
Okay, so answering the first question is how we're going to do it for the clients. First of all, let me tell you that we haven't implemented Vivaldi Coordinates ourselves. We have used Surf, which will have Vivaldi already implemented in it. So it's already a tool that will give you one of the benefits of Surf is basically it will offer you Vivaldi Coordinates. So this is how this thing is implemented. Now, how it's implemented exactly, whether it is peer-to-peer or whether it is beacons, to be honest with you, I haven't went to this technical informations in Surf to know how exactly this has been implemented. Now, I have modified the code of Surf to a certain point where I have understood how they are going to do the calculation. But to be honest with you, I haven't went to the technical level of understanding how the communication for implementing this gossiping algorithm is done. Well, I've just used a tool which will give me the Vivaldi coordinates, and after that, I use those coordinates in my calculations.
Okay. Well, it's likely that this tool, if it implements the coordinate as they are described in the various papers, would require the nodes to communicate themselves, which you will certainly agree that between clients it is not a feasible thing, because they would have NATs, they would have firewalls, they would have restrictions to the entering connections. So, but yeah, if it's something that you used, and I understand that this is not one of the contributions here. So that's, but I wanted to clarify.
But let me comment on one thing regarding the firewall, because actually everything and proximity was implemented in IP tables, which is the firewall for Linux. So in fact, we had control over all of this. Now, to be honest with you, in terms of self, I didn't see any recommendation about changing the firewall. So I'm not sure if it's exactly peer-to-peer. Maybe it's, as you said, beacons.
It is possible. So there are implementations. So they might say Vivaldi because it's kind of the name, but there are optimizations where instead of connecting nodes randomly, you just connect to 3-4 known locations that are well spread out, like geographically, and then you would bootstrap your coordinates this way, and it works much faster. I would not be surprised if it is an up-to-date implementation that it does something like this. This is what I meant by these beacons. Essentially, you just, if you have a few sites, 4 or 5 in different countries, then you can just measure your latency between you and those sites, and you would bootstrap your coordinate. In fact, it is questionable whether you need to have these peer-to-peer communications to update your coordinate afterwards. Very often, the location you get, the coordinate you get in the first place is good enough, unless you have mobility. But okay. So I have another question. So at some point you mentioned in the presentation that one of the targets would be games or augmented reality. These are applications where different clients may need to connect to the same location, to the same edge instance, because essentially, if you have a game, for instance, it's clearly that if we are playing tic-tac-toe together, then we need to access the same location. Would it be something that would be easily implementable in your solutions, like having users connecting to attached to the same preferential site, or is it something that the application developer has to implement all by yourself?
So I guess at this point, if you want to, let's say, play tic-tac-toe with somebody, multiple play games, normally what will happen is that you're going to connect to the application first, and after that, the application will give you the coordinates where you have to connect. So I guess it's something that should be connected by the application developer. And after that, I guess our contribution here would be beneficial to decide which is the best node. For example, we can take a future direction where we can say that it's beneficial to decide, oh, actually, this is a very good idea, to decide which node is the best or which replica is the best for those two users to connect at the same time. So yeah, I guess it's something between the infrastructure and between the application. So in the infrastructure, it can offer them a solution for this, and for the application developer, you have to organize how the users will be connected to the first front end, let's say, of the application, and then how they will be redirected toward another replica or another component.
That was the essence also, is like, indeed, the application can handle the fact that you have this shared state and so on. This is one of the assumptions you make, but you don't want the replica to be very close to one user with good QoS and the other being very far away. You need to find some middle ground, and this is where the proximity, for instance, could actually take that into account. It's like it's not being as close as possible, but being fair to the different users. I only have two questions left. So I have actually a technical one. So on page 114, you don't need to open the document, but you mentioned operation scale down operations. So this is in the chapter about Voila, I think. So you say that, so you describe in detail the scale up operations, but scale down is not as detailed. And you say that when the load grows below the threshold, you need to identify a replica. I'm quoting you, identify one replica that can be removed without violating the QoS constraint.
Yes.
So I would like to hear a bit more about how you actually do this. So what is the method you use to identify the victim replica when you need to scale down? Is it...
So let me speak about the scale down algorithm. So at the beginning, the question is not only what replica we want to remove, but it's also when we want to remove. I guess this is the more important question in the scale down algorithm, because the last thing that you want is to scale down and suddenly you will have a quality of service violation. So we are going, first condition that we have to apply to scale down is the fact that we haven't had violations after a certain number of cycles. So we have studied this and there was no violations for, let's say, 3 cycles. And after that, we have the possibility of scaling down. And then we have a metric that we are going to calculate, which is basically the resource utilization. So whenever we reach a certain threshold in the resource utilization, we will start saying that, okay, because we haven't seen a violation and because we have this low resource utilization, maybe it makes sense for us to remove one replica. And after that, how we are going to do this is simply by taking this replica placement and by testing simply each placement and removing one replica from this placement and what's the value that you are going to get. So basically, it's a simple idea is a very simple mechanism because in this case, we don't have this complication in terms of finding a placement. In fact, here we have very limited placement that we can try, which is basically removing one replica from this set. So we have very limited, which is the complexity is n. So we can do it in this way by just trying and after that removing the best replica. However, here the scaling down algorithm is recursive. So basically, we will try removing one replica at the beginning by finding that okay, this placement while removing this replica will give us the best quality of service or the higher value of quality of service. And after that, we are going to keep moving by removing more replica until we reach a point that, okay, we cannot remove more replicas. So this is how it's implemented.
Okay, thanks. So I think I'm actually done because the last question I had was already asked. I will stop here. Thanks for your answers. And I think I can
thank you very much
for the next one. Thank you very much.
Thank you very much.
Thank you, Etienne. So now we have examinators in the jury. So Shadi, can you please start your questions?
Okay.
I can put my mask.
Oh, that's fine. So thank you very much for the nice presentation and congratulations for your work. I mean, you have clearly like discussed the state of the art, and you have demonstrated not only the innovative aspects of your work, but also the practical aspects of them. So congratulations for that.
Okay.
Now going back to questions. Actually, the first question came in my head that you have implemented all your solutions in Kubernetes, and you have evaluated that on a real testbed. I think you built it yourself. So what was the major difficulties in the complexity of such implementation? And on the other hand, if you are thinking about porting or implementing, integrating your solutions in different orchestrator system or engine, what will be the difficulties, the complexity, and how much work or what it will take to integrate it in other systems?
That's actually a very good question, and a question that I would really like to explain, because like I will explain how much I suffered while just like doing this. Okay, so your question is basically how much complicated this engineering task was.
Exactly.
So first of all, let's agree that this is an engineering task and it doesn't have a research value. However, the research value that you are going to get is basically by saying that you have implemented this inside Kubernetes, which will give our algorithm a certain feasibility. So I would say one of the most hard tasks to do this was understanding the internals of Kubernetes or understanding the internals of any orchestration engine. So to understand how you're going to implement the routing mechanism, you should have a really good idea about every aspect of this internal inside Kubernetes. So you need to understand how kube service works and how the REST communication works and how the API to API server send the messages and how the routes are implemented, whether it's in IP tables or whether it's in IPVS. So I guess whenever you understand all of those, then you will have the other engineering task of figuring out how we are going to tweak the system. And I would say this is a less complicated task whenever you understand everything. But yeah, I guess in this case, understanding the internals in detail of Kubernetes was one of the complicated engineering tasks that I had to do to implement those in Kubernetes. Now, in terms of implementing those solutions in different orchestration engine, I have a small experience with, I told you, because we have been communicated with, like we have a request from somebody in India who want to implement proximity and nomad.io. And to a certain point, I have seen that at this point, whenever I have done it in one of the orchestration engines, and I have to understand to a certain point how those orchestration engines behave, I was able to at least identify exactly where this have to be implemented in a couple of hours. So at this point, it was much easier to understand all of the components. And to a certain point, this is relative to the orchestration engine. So for example, in nomad.io, which is by HashiCorp, I guess the company, which also created Surf, that's why I was able to understand a little bit faster. But for Mesos or for Docker, to be honest, I haven't tried, but I would say that it is not complicated, it is time consuming. So at a certain point, you'll understand how this orchestration engine works, and at a certain point, you will be able to implement it. But you need to pay attention while you're trying to implement such features.
Cool. So now going to more technical questions. So you mentioned that you're using heavy tails or tail latency as some kind of metric, which can help you to guarantee fairness between different users.
Yes.
So this is a very nice idea, but did you evaluate fairness as independent metric? Like if you have multiple users and you can try to see how much fair it was, your solution was to different users in like dedicating the resources or reducing the latency for each of them?
Okay, that's a very good question. So first of all, we have used tail latency, where our purpose is to eliminate the tail. So whenever we reach a point where we are going to eliminate the tail, then we can make sure that at least the application will perform almost equally between different users. However, since we have this distribution, it's a distribution. So basically, we are going to see that already some users are going to have lower latencies than other users. But what we are going to make sure that won't happen is the fact that some users having a latency greater than the threshold, which will affect the quality of experience. So yes, we will have, that's why we didn't use fairness because we know that there will be no fairness. This depends on the location of the user and in the location of the nodes, for example, and the latencies between the nodes. So we don't have control over all of those to ensure user fairness. But we can make sure using tail latency that all of the users will have well-performing application.
Okay, cool. Something else in slide 26. Actually, you don't need to go there. So you mentioned that you tried to detect slow nodes or slow nodes or requests according to their proximity or saturation.
Yes.
So, and for each of them, which is very nice that you are trying to identify the root cause of why the nodes are or the requests are slow.
Yes.
And on the other hand, for each of them, there will be some kind of independent or different action. So did you measure the cost of different actions? I mean, for sure, if you have some kind of a proximity problem, in that case, you need to find a new pod in some approximity measure or distance. While if you have some kind of saturation, you need to replicate the pod or replicate the application. So there is different cost or it's equal cost? And did you measure, for example, the impact or the improvement under different let's say, root cause of slow requests?
Okay, so you mean the cost by the resource utilization?
Exactly, and also the improvement if you have, if the main cause would be some kind of a proximity problem or the main cause of the slow request would be the saturation.
Okay. So for this question, first of all, we didn't calculate exactly the cost of doing this. We tried to minimize the cost by trying to stop as soon as possible and trying to do replacement instead of autoscaling directly. However, to answer your question here, this is a realization more than evaluation. So we have seen, and whenever we were evaluating this system, that we will have, in the case of proximity, most of the time we will see that we have a new source of traffic. And this means that, okay, maybe we can change the replica placement in a certain way to include this new source of traffic and to solve this proximity violation. So most of the time in proximity, if there was enough number of replicas, we can solve it by just replacement. And now, however, for saturation violation, where we suddenly have an exponential increase in the number of requests, we will reach that. In fact, the number of requests is greater than what's available for the, so basically it's greater than C0, which is the capacity, times the number of replicas. So definitely we are going to increase. So that's why we would say that for the saturation violation, normally it's more costly, because most of the time we are going to increase the number of replicas. However, for the proximity violations, in some cases, it's easier for us to do a replacement without increasing the number of replicas. However, this is very relative. It depends on the case itself. And here, mentioning this question, in fact, recording the cost and regarding the saturation violation, we have seen that in this case, something that we didn't present, maybe I can show it to you on the slides. Something that we didn't present in the presentation, but in the thesis, is the fact that later on, so whenever we look at this slide, we will see here that this saturation violation is huge. So how we can avoid the saturation violation? Simply by scaling up before we reach the saturation. So this has also have been implemented, and after that we were able to, in this case, we were able to say that, okay, we have a safety margin, which means that we are going, in this case, for 10%. Before we reach the maximum utilization by 10%, we are going to scale up. So this is also something that we have done in terms of saturation validation.
Okay, great.
Thank you.
So last question,
It's
and
okay,
then I will.
So
actually, I like the 4 future directions that you have presented in the last slides. And my question would be somehow, I don't know, tricky a little bit, or maybe for the benefit of future direction of research about your work. So if you have time, for example, or if you want to advise somebody to work on one of the 4 directions which you presented as future work, which one you will choose and why? I mean, you have mentioned something about federated learning, introducing cost, heterogeneity by like using accelerators and so on, but which one you will advise or you will go with and why?
Okay. So in this case, actually, the answer is very obvious, I would say. That the future direction that I would suggest, other than the one that we are working on, is the microservices. Because in the other cases, we are suggesting a case that doesn't exist until now. However, in the case of microservices, even though it's the application model that we need to change, but however, it is an application that's already found and the fork which we are already creating. So this is the case that I guess will be relative very, very soon. This will be like relatable very soon. So I guess in this case, to have a complete set of, and to cover everything related to proximity awareness, the first thing that we need to start targeting is the application model and application architecture. So I guess if Guillaume wants to replace me with another PhD, even though that's hard, I guess he should work on the application model. He should work on the application model and the microservices.
Great. Thank you for your answers, and again, congratulations for your thesis.
Thank you very much.
Thank you, Shadi. So now, Eric, please, can you ask your question?
Yes, thank you very much.
Thank you.
And thank you very much for a nice reading and a nice presentation here today. And I would like to focus, at least in the beginning, mainly on a few things that relates to the realism and the implications of the work, or sort of the starting point for your work, basically to understand what are the impact of these limitations and restrictions. Since it's always like that, you always do some restrictions and assumptions that limits your problem in research, but then you also want it to be possible to generalize it to the real world when you have the results in the end. And so I don't assume that you would ever do research on the full-scale, totally complex situations, but rather that your results should also be applicable to those.
Mm-hmm.
And the first starting point would obviously be the applications, but now there were quite a lot of talk about that from both Ivona and Etienne, so let's keep that short. But they proposed some, put the words in your mouth about some applications, but what applications did you have in mind when you started with this? Are they the ones that you have been talking about here with them, or did you have other things in mind?
Okay, so the first vision that we had for an application, which we know that it's a limitation whenever we speak about the application layer, was simply an application where we have a service, and this service we are going to send a request, and this request will be calculated and will be returned. So the application that was in mind is a computational, monolithic, service-oriented application. So basically, we'll send a request, for example, for computation. Let's say we can send an equation to a certain service, and this service will compute those parameters in a certain way. So basically, for example, we can say you are doing image analysis, for example, and after that you are going to send an image to be analyzed in a certain service, replicated service, and after that we are going to give back the result of this analysis. So this is the application that we had in mind at the beginning. So anything related to, for example, VR, which is not with multiple people in the VR. So VR, let's say, or augmented reality, where you are connected to a service that will tell you that will give you a feed with certain things that are implemented inside the feed.
Mm-hmm.
Yeah. So this is the main application that we had in mind.
So the reason for asking is that on page 25 you have these limitations that are two limitations that are quite substantial. Where the first is that you consider that data consistency between the application replicas should be a responsibility handled by the application provider and transparent to the full computing platform itself. So this is, of course, in the general case, a very strong assumption. If you talk about stateless applications, for example, which you mentioned previously here today, then this problem doesn't even exist.
Yeah, we consider that that the application that we are handling is stateless at this point. So this is actually this is one of the limitations. But I would like to repeat the fact that we were focusing on the infrastructure, and we believe that whether this application is limited by the limitations that we have defined, or whether this application is similar to what we have defined, we are still need to optimize the infrastructure layer that's underlying under the application. So if this application is stateless and does not need consistency, or is it monolithic, we are going to need the infrastructure. And whether this application is microservices or serverless or stateful, then we are going to still need the optimization in terms of the infrastructure. So that's why we have targeted the infrastructure first, because we believe that this is the base of the problem. And after that, everything related to the application is a limitation, of course, but this is the continuation to complete the proximity awareness on all of the levels.
Mm. Yeah, so let's move on from that, since it has been a lot of talk about that already. One other thing is that I think was very clear during the presentation here, that in your experiments you do things, for example, you emulate the network parameters, the latency to different places, but you actually built a system that is meant to be running in the real world. So what I would like to understand is, so when you do the management actions, and you say that you use based on latency and processing capacity, these are the requirements you look at. What metrics are you actually getting from the system to do that?
Okay, so the first metric that we're going to get from the system to calculate those parameters, the latency, is the latency, basically the latency for the route. So we will calculate the latency from the gateway node to the hosting node, and this should be under a certain threshold at 0. And for the case of the capacity, we're going to calculate the number of packets per time unit.
But you only consider then the network latency and the network aspects of the capacity.
Okay, so do you mean by that have you considered bandwidth?
So do you take the compute into account?
I'm sorry?
The compute capacity?
We have the compute capacity. Okay, so we consider that the pod have limited resources allocated to it, and after that, those limited resources, whether it's in terms of memory or in terms of CPU or in terms of storage, this means I don't think it will be storage. I'm sorry, but whether it's in CPU or whether it is in RAM, this means that we can process a certain number of packets per time unit. So this value also is decided by the end user, by the application developer, because it's application specific. So have I answered your question?
Yeah. Yeah. So this comes to where I was a bit confused. So the experiments are run only with single applications, as you just said, for clarity, but the system is really meant to be also for multi-tenancy. So then you would have other applications also competing for the same CPU cycles on the same physical hardware.
Okay, so I guess to answer your questions, this is to a certain point at the hands of Kubernetes more than at the hands of ours. So here it will be related to how much capacity you will have per node. And after that, we have this calculation in Vola and in Hona, where we try to distribute those replicas as much as possible. However, in Kubernetes, what I believe is that it doesn't matter how many replicas you have, as much as they are idle, they are not using resources. So it depends also on the number of packets that you are going to receive per replica.
So what I try to understand is basically if this metric is an application level metric or an infrastructure level metric that you're using.
I would say it would be both. I would say, because it is related to the infrastructure where we have the resources, and it's related to the application where different requests will have different processing necessities. So if we are computing something for AI, it will be different than computing something for much simpler applications. So I guess it will be controlled between both. Depends on your hardware and it depends on your application.
Mm. Yeah, so we'll get back to that when we talk about doing the management operations and who actually has access to different information. But I have one other question relating to, so it's quite common in particular for like video applications, video streaming and so, that you adjust the quality of the application when you don't have the capacity that you need. For example, you reduce the resolution, you might even reduce the frame rate if it's a video. You can also do similar things for compute capacity, that you reduce the amount of content you provide if you don't have enough resources.
Okay.
So in these situations, then the application would adjust to a smaller amount of resources.
Mm.
Would your system be agnostic to that, or would it be fooled by such a situation that you think that capacity is now sufficient since you don't use more of the network, but you have actually reduced your usage due to the fact that it was limited?
Actually, this is very, very, very interesting approach whenever we consider, because you have considered one single variable that will be decided by the end user. However, what you are saying exactly here, where we have levels of quality of service constraint. For example, whenever we have a certain load, we can give this certain quality of service. So I guess no, we haven't implemented something like this, but I guess it will be very interesting future direction.
Mm-hmm. Do you have, if you understand, if you take the network part of the problem, so I assume that you reduce the resolution and send less data in your video stream due to the fact that you have less capacity.
Mm.
What would your system do then?
Then at this point, what you need to change is the fact that the value of C0 that you are using, because you are using lower resolution, this means that you are going to have a higher capacity. You can receive more requests per pod. Have I answered your question?
Mm-hmm. Yeah, but ideally you would like to have more bandwidth so you can run at full resolution. So the fact that you went for lower resolution was basically a fix to keep the frame rate. So
here, what you mean exactly by the bandwidth of the network or the bandwidth of something else? The network bandwidth. So we didn't, to a certain point, we didn't consider the network bandwidth in our work. And I guess at this point, it will be something very specific to the application whenever we change the resolution. And to be honest, I don't know how exactly we can do this relation between the resolution and the bandwidth network.
No, yeah. I think this comes to where I'm going, that this interplay between the application and the infrastructure is always making life harder than we want it to be. So you at some place claim that full computing, like cloud computing, enables a clean separation of concerns, and then you separate software developers from infrastructures or infrastructure providers, and that you also claim are automating and managing the applications. And as I say, unfortunately, my view of the future is that this is possibly much more complex than that. So I would like to go through a couple of things and see how you think this would impact your situation. So first of all, in the fog infrastructure, so the total infrastructure with both fog nodes and cloud data centers, I would assume that the infrastructure actually is owned by several parties, that you have a few number of mega scale data centers or cloud providers, and that they are complemented by telco providers that provides the fog nodes here to the end users. You might even have small data centers in between that are either owned by telco providers or cloud providers. And then to that, I would like to add application owners that are possibly the ones you consider the software developers, which would probably then have contracts with the customers, and they would have the insight on what the application is doing, how application-specific metrics change over time, etc., which could be like the parameters I just asked about. And when we look further into these scenarios, we also often consider the situation that not all application owners have the contracts with the same cloud providers or telco providers. So you have a bunch of different application owners. They have own contracts with different subsets of the infrastructure providers. And then you want to manage all of these applications anyway. And you typically don't want to reveal so much of the information. The infrastructure providers doesn't want to tell how high load they have on their infrastructure. The application owners doesn't want to tell too much about what happens in their applications. So if you then say that you have a simplified scenario, first of all, would you agree to such a scenario, or am I just making life too complex?
So I guess life is already too complex, but I believe that yes, definitely you will have applications that will have different requirements in terms of the infrastructure and in terms of what they want to do exactly. But however, here I have to mention that in our scope, we have mentioned that we are targeting latency sensitive applications. And what we have tried to do exactly here, whenever in terms of requirements, we try to take an application specific requirement, and after that we handle everything in the background. So at this point, whenever we have more than one fog provider and more than one requirements at the same time in terms of bandwidth and in terms of the infrastructure, I guess this is a little bit away from exactly the scope of my PhD.
Mm-hmm.
So for my PhD exactly, I have mentioned that we are targeting latency sensitive applications in scenarios where it's implemented in fog. Now the question is whether it is we have more than one fog provider at the same time, whether this is affects or not. I guess it doesn't affect, because at a certain point we will have a certain level of abstraction in terms of networking, where those nodes, no matter from where they are connected, they will be connected using a certain abstraction layer. For example, in the case of Kubernetes, we will have the container network interface, the CNI, and in this case, we don't care exactly from where this node is connected or not. So this alone is another research question. And whenever we have different types of requirements, to be honest with you, I'm not trying in my PhD to target all types of requirements that we can solve and for computing. We were just focusing on latency sensitive application, and we have seen that this feature, which is proximity awareness, should be implemented in a certain way and for computing.
Mm-hmm.
So have I answered your question, or do you want me to elaborate?
I think at least to some extent. So I think that the main questions are probably around the fact that you can't do the management from one infrastructure provider that knows everything about the infrastructure, since it only owns part of it, and then there is someone else owning other parts. And also that you have some information that belongs to application owners, some that belongs to infrastructure providers. And in your work, you assume that the infrastructure provider has all the information. And I'm not sure how difficult it is to generalize this to the case that when you don't have all the information about things, or how much the outcome will be limited by the fact that you don't have all the information.
Okay, excuse me. First of all,
we are at the point where that we don't have a fog platform. So I don't know how we have shifted from the case where we actually have one fog platform that we are working with to having multiple fog platform and to having this problem of privacy that each fog platform, each fog provider want to limit the knowledge from other fog provider. So I guess at this point, we need to focus on solving the problems whenever we have one fog provider, and later on we can take into consideration where we have more than one fog provider and the federation that we need to solve. So of course, this will create a new research field, I would say, in terms of the privacy and in terms of having more than one provider. The same way that we have those research questions and the clouds, where we have cloud federations. This is, I guess, it's a completely different PhD to answer this question. That's why we have actually considered in the future work that, okay, maybe at a certain point in the future, whenever we start having a fog platform in the first place, maybe you are going to have more than one fog provider, and at this point we have to handle such things. However, at this point we are, I guess it's very, very early question for me to answer.
Yeah, and as I said in the beginning, I never assumed that you would solve anything for the full maximum complex case, but rather what I try to understand, that is basically how far have you come towards that case. So the problems you have solved in your controlled environment, how much would that solve of the difficult problems? So this is where I'm going. So, but I'm fine with the answers. So,
okay.
So yes, don't take me that I'm criticizing or anything because you didn't go for this full case, since that would be stupid and you wouldn't be here today if you would have started with that case.
Yeah, well, like I guess here I have to mention that I forgot what I have to mention. I'm sorry.
Yeah, I just have a final implication question on that is really this is really off what you have been doing, but you might have some thought about it. So you in cloud scenarios, there you have typically have the autoscaling functionality being something that has been in the control of the application owner. And I guess this connects to the business models that you pay for the amount of virtual machines you allocated. So then it doesn't make sense to have, for example, Amazon deciding how many virtual machines you should run and then just send the bill. Instead, you have the application owner deciding how many to run, but then the Amazon is doing the scheduling. But in Voila, then you do also the scaling on by the infrastructure provider. So you basically just guarantee some performance and then ask someone to pay the bill. Have you had any thoughts about what implication that would have for the business models?
Okay, so first of all, this business model is not new, because in the case of Amazon, for example, you have the AWS where you can reserve virtual machines, and you have Amazon Sail where you run a certain service. So this business model already exists. I guess it's Sailboat. I'm not exactly sure about the name, but in Amazon they have this feature where you just decide and declare what do you want. I want this specific service, and it will give you, and Amazon will manage the pricing. So I don't see the problem here. And in terms of the business model, whenever it comes to the cost. So in terms of pricing things according to the number of resources that you are using, you can price things according to the quality of service that you are requesting. And I guess something like Amazon or something for provider or in the future should have the capabilities of predicting how much this quality of service will cost. And as the result, you can cost according to the quality of service that are related to the application, and not according to how much physical nodes and physical CPU and physical RAM that you have reserved.
Okay, very good. So let's go for one more detailed question on the HONA algorithm.
HONA?
So on the HONA algorithm.
Okay, so basically the second contribution.
Yeah, exactly.
Okay.
Since I was involved in the third, I didn't want to ask about that one particularly.
Okay.
There you talk about doing the decisions, one replica per application and cycle to avoid oscillations.
Yes.
And as I understand, you also make the decisions one by one, right? You make the decision for the next action. You don't make a plan for multiple actions. Is that, do I get that right?
Yes, that's right.
So can you say something about the oscillations you try to avoid?
So basically the oscillations that you are going to try to avoid is whenever you have change a lot in the placement, maybe this will create certain oscillations because you don't know exactly if you are going to. You have some users which were offline, and after that, I guess something related to specific to HANA in this case, because when we moved to Voila, we changed the way that we are going to do those oscillations. So nowadays, it's not only one replacement that we can do; it's more than one replacement. And second, I guess the oscillations were basically the main reason why we changed only one pod at a time was basically the fact that for Kubernetes to change all of those at the same time, it may be complicated in terms of the technical implementation of this.
Mm. Yeah. But then with Voila, there you look a bit more ahead. You look at create a set of pods that could be replaced. And I guess this also involves then making more of a plan of actions to make ahead. So instead of just doing one action, deciding right now one action, you can decide on a series of actions to reach a certain goal state.
That's actually a very good point. We will take this into account.
So, but you took some steps.
Then the time is flying. So last question, short one.
Okay. Yeah. So final question. So if I would ask you what you are most proud of, that would probably be that you have created this full stack management system. But given reality where it's very difficult to get someone to take over a whole solution coming from research and replace what they're running, it's much more likely to find someone that would pick out some scientific contribution of yours. So if you would try to focus on that, could you highlight one scientific contribution that you are most proud of and where you have the highest hopes that someone else will pick this up and put it in, make use of that in their own systems and for their future research?
So this is actually exactly similar to saying which one of your babies you like the most. So I guess in this case, I don't know. I need to be diplomatic. I guess every one of the solutions that have been implemented have a certain novelty on them. But I believe at this point that the most important thing is the implementation in terms of Vivaldi in the proximity case. And I guess Vivaldi is very generic in terms of the routing, and it's very distributed. So I guess, and we are still at the point we are receiving some questions about implementing this to a certain point in production. So to be honest, I would say that maybe whenever it comes to industry, maybe proximity have certain benefits. However, the other algorithms, I would say that maybe they would be better optimized solutions.
Okay, thank you very much, and thank you for a very nice discussion.
Thank you very much, Eric, for your interesting questions.
Thank you, Eric. So now, Guillaume, as the PhD advisor, do you have any questions, any comments?
So, of course, I have lots of questions. I've never had time to ask you all those questions in the last 3 years. No, of course, I will not ask any questions. I just wanted to say how much of a great pleasure it has been working with you. I still remember when you applied for this PhD position and you thought I was not answering fast enough. And you literally harassed me, saying, give me that position or answer me. I think that defines you very well. Like, you know what you want and you find the ways to get there. And it also applies to your research. So honestly, it has been a pleasure working with you on all those great topics. The thesis ended up in a place where I did not anticipate we would end up when we started, but that's the normal thing of any research. It is great to see that your work is being recognized and that you have high-level publications. Now, I must say this.
Yes.
There's just one thing I still need to ask from you. Not a question, a request.
Okay.
Stop calling me Professor Guillaume. Just Guillaume would be good enough.
Okay, Guillaume.
So that's all for me.
Okay, thank you very much, Guillaume. It was really a pleasure for me as well to work with you. I guess I'll go to postpone the thanks for after the deliberation.
Okay, thank you, Professor Guillaume. So, okay, I will have some just one question. Okay, to finalize this part of the question. That is less related to what you worked on. So you did great works and proposed implementation algorithms and etc. And so I would like to have your point of view about security aspects, all right? And for instance, you have designed routing algorithms that are based on tail latency, all right? So, and decisions are taken according to tail latency. Okay. And so my question is, what is your point of view? Did you think about attacks that you may have on your system, and in particular with malicious behaviors that can generate fake traffic or have an impact on the tail latency, and then finally control the decisions, the routing decisions that may occur thereafter?
Okay, so answering the question of security, first of all, the question of security is not only a concern for my work, it's a concern for fog computing in general. So we have seen that actually there is a lot of challenges in terms of security in the fog computing, and mainly is the way that those end users are going to access the fog. So as we see that in fog computing, we have one central entity, and after that we have the end users connecting to this central entity. At this point, it's super easy for us to create this high firewall that will detect a lot of things. However, whenever it comes to in terms of computing, it will be anti-productive for us to, let's say, route those requests from one place to another to be checked before going to the nodes. So here we have a problem in terms of end users connecting to the nodes themselves before they request for the access layer or the access network, how this will be handled exactly. Now, in terms of my algorithms, I would say that we will have the same concerns regarding the security, but I don't think there's something very specific to my work regarding security other than the things that you should expect in any case scenario in terms of networking or in terms of any system where you may have some people overloading to a certain point the system. So yeah, I guess the main concern is the access network, and after that, I don't see that there is something specific to my work in terms of security.
What will you do if tomorrow you have to think about this kind of aspects? Do you have already some ideas or some?
In terms of access network, you mean?
Yeah, and in terms of fighting against, I don't know, malicious behaviors, even if users are well authenticated for your system, they may perhaps have a malicious behavior to try to
so I guess
the system.
Okay. So I guess this depends on the privacy itself of the fog networks, fog clusters or fog platforms. So basically, we can see that we have some fog platforms which are private, and we have some fog platforms which are public. So in the case of public, I would guess that we have a concern in terms of somebody who will overload or execute some kind of DDNS or something like that, denial of service. And I guess in terms of private, the main issue that we need to focus on in this case, I would say if it's private and have something sensitive, for example, for military or such applications, it would be something like man in the middle. So we need to figure out exactly how to act against those algorithms. So the main challenge here would be the fact that we cannot create something which is very centralized, because this centralization would affect the latency in terms of everything should be checked at the central node, which will affect the latency. So I guess it should be something distributed first, and I guess it should be something that won't be running continuously. It should be running at a certain point to check the current situation. So this is like the first imagination that I will think of when I'm writing for security.
Okay, thank you very much. So we're ending this session part. And so we are going to brainstorm about your defense, and we have to change the
Yes. So
the visual.
So for the committee members, can you please disconnect from this Google Meet session, and we have another one for deliberation.
Okay.
And maybe you stay on that one because anyway you don't have the other, and we will rejoin when we're ready to announce the results.
And change the figure.
Okay.
Yes, and
See
change
you.
the background. Now we will also stop on this one.
So I should leave now.
So Mehdi, I think you can switch us on the YouTube live again. Yes.
Is this the natural cable?
I think it's the same. But otherwise, don't bother. I'll just stream on my phone. No, this is not good. The Wi-Fi will filter Google Meet.
Okay.
Don't bother. I'm streaming from the phone.
So can I just because I want my family to see it in proper way.
They will see it.
Okay. Somebody is now streaming. Okay. So just if it's ready.
Yes.
Okay.
Go
Okay.
on.
It's actually connected, so we can connect. Okay.
We cannot hear. There is no sound. Can you switch on the mic?
Yes.
It's fine. Thanks.
So you gave a clear and pedagogical presentation. You made and you present your numerous contribution in the field of fog and cloud computing, and you provide an excellent overview and complement to your thesis manuscript. And so you covered the full set of your contribution, and you did the presentation very well structured, and you addressed the topic topic that is very timely and relevant for science and society. You have successfully answered to the jury's many questions, and you explain your choices, and also you provide a better understanding of of the advantages and limitations of your scientific contributions. And you have also demonstrated your mastery of the field and the many skills and the many skills that you have on the topic. You also have showed your maturity on the issues that you have addressed. Finally, the jury also wishes to underline the breadth and richness of the work that you have carried out. And you do not only propose new concepts and algorithms, but you have also implemented them and also evaluated your work for simulation and deployment in a reference industrial system, which is remarkable. Further, the jury would like to appreciate your meaningful contributions. And in conclusion, and after deliberation, the jury unanimously consider that you are worthy of the title of Doctor in Computer Science from the University of Rennes with the European label.
Thank you very much. So I guess it's the time for me to thank everyone. So first of all, I would like to thank the jury, every one of them, for attending. Thank you, Mona. Thank you, Eric. Thank you, David, and thank you, Shadi. Thank you for attending my PhD thesis and for taking the time to watch my presentation. And thank you also for reviewing my manuscript and giving me the very valuable feedback in your report. Here I have to also thank my supervisor, Professor Guillaume. I will be losing words here whenever I describe Professor Guillaume as a supervisor. I would say that I wouldn't ask for anything better than Professor Guillaume Pierre. Oh, I'm sorry, better than Guillaume, in terms of his supervision, in terms of how he treated me during those 3 years. He was very flexible with me. He gave me my space to work, and at the same time, he gave me great guidelines and great guidance in this thesis. I have to specifically highlight his work ethic and his attention to details, which is very, very useful. And also, I would also say that he always provided me with continuous support and continuous care, and I'm always grateful for that. And here also, I want to say that Professor Guillaume and his supervision have made me reach my maximum potential. So I really would like to thank you for all the time that you have contributed toward my development as a researcher, as an engineer, and also as a student. Thank you very much, Professor Guillaume. Now I have to thank here Professor Eric Elmroth for, first of all, hosting me at his institution or at his research team in computing science lab at UMI University. This experience was very, very fruitful. I have seen the research culture at UMU, and I've been in contact with a lot of amazing people there. And the input and the knowledge of Professor Eric have impacted this PhD very positively. So thank you very much, Professor Eric, for hosting me at your research team. And forward, also, I want to thank Shadi and Cedric, the members of my CSID, for giving me the advices over those 3 years and for guiding me and steering this PhD toward where it is now. Your input were very, very, very useful. And here, let me thank Shadi for all of the discussions that we have. It was really nice to have a technical discussion in my native language with Shadi, and it was really enjoyable having all of those times where we are discussing in the balcony. And here also I need to thank, first of all, the members of the Myriads team, the members of the Fokuru project, and the members of the research team in the computing science lab in OMU. Thank you very much for all the discussions that we had. Thank you very much for all the advices that you gave me and for the help and for being very hospitable. Here I have to specifically highlight the relaxed environment that have been provided here in INRIA and our team in Myriads, and also the friendliness of all the teams and all the people that have been working with. And here I hope also to specifically mention Milian Pouquet, who was my teammate, who helped me a lot technically, and also my other teammate, Francois Lemercier, who also have helped me a lot in terms of different issues, in terms of the discussions and in terms of the French system and a lot of things. And I would like to thank Louis Guégon, my friend in the team, and Durra, and Mehdi, and Hamid, and Arif. And I'm sorry if I'm going to miss someone, but I would like to thank all of them for being there next to me and for providing me this professional environment where I was able to thrive. Also, I want to thank my friends in Sweden and France and Lebanon, who have been with me and stood with me during the highs and the lows of my PhD. Thank you very much for giving a flavor for this PhD. It was really a better experience with all the interactions that we have and all the memories that we have. And here I'm going to get very emotional, but finally and most importantly, I would like to thank my family. I would like to thank my father, who have always instilled those ambitions and those curiosity in myself.
he have always been providing me with everything that I need to excel in my field, and he have always been motivating me to do everything that I want, if it's legal, of course. And and I would like to thank my mother as well. I will always say that it's like her care and her love have been reaching me when I was here in France for the past 3 years. And without her patience and love and care, I'm always a better version of myself because of all what she have done for me. And also I would like to thank my brother Imad and my sisters Isra, Ghadir and Asil for being next to me and supporting me through over those 3 years. Thank you for supporting your little brother since the first moment, because I'm the smallest. And thank you for being next to me in those three years. And here, I wish that I had made you proud. And I'm sorry if I've missed someone, but of course, this work have been possible because of a lot of people. And I would like to thank everyone who have contributed positively toward the successful finish of my PhD. So thank you very much.
So we cannot shake hands, boss.
But yeah, why?
Congratulations.
Yeah, it's a little bit sad.
Congratulations.
Thank you very much.
Okay, congratulations, Ali. Very, very well deserved.
Thank you very much.
Congratulations also from my side, and all the best for the future, whatever you are doing now.
Thank you very much, everyone. Thank you very much.
So I think this concludes the defense. We're going to disconnect the telco. Mehdi, don't forget to stop the YouTube live. And thank you all for attending.
Thank you very much.
Bye-bye.
Bye-bye.